We want internal loads at C. And we are given these two external forces that are being applied. We're given F1. $350J minus 400K. And F2, we're given 150I minus 300K. For this example, I am going to move the coordinate system, or the origin of the coordinate system. I'm going to translate it so that C is my new origin, just so it's a little bit easier to do the rest of the analysis. So I'm translating this 2 in the y direction. C is my new origin, and I'm not going to rotate it, so Z is still going to be up. X will be down to the left, and Y will be down and to the right. And I'm keeping, again, everything to the right of C. I copy everything that was affecting that piece of my picture. So I have F2 acting on the pipe, and I have F1 acting on the pipe. I'll just leave them labeled F1 and F2 since I did write them up here what their values were. Those are the external loads. Now at C, this is where I have to include the loads I can now see that were keeping the material together, that when the pipe was whole were not visible, but now that I'm detaching it from the rest of the pipe are going to come out in the picture. First thing I want to look at is the internal normal force. Again, my cut is the XZ plane cuts through my figure here, so that means that my outward normal force is going to be along the negative y direction. So P is directed in the negative y direction. Now that I know the direction of my internal normal force, I can draw the torsional moment. It's going to be if I put my right thumb in the direction of P, the way my fingers go is going to be the direction I assume for T. Or I can more easily represent it as the double head arrow like we saw in chapter 4 and call that T. Either representation is fine. I think in 3D this sometimes is a little bit clearer, the direction of our assumption. So T is positive around the axis determined by P. P is coming out from that cut surface. Right, so those were both determined by the surface of the cut. Now parallel to the surface of the cut, I'll have two components of shear force, two components of the bending moment. Again, the XZ plane determines that cut surface, so I can draw one component of my shear force, VZ. I'm going to assume it's in the positive Z direction. I'm going to assume that Vx is in the positive X direction. Also around the X and the Z will be my components of the internal bending moment, which I will also assume positive directions for. So Mx, assume positive around the x-axis, and Mz, I'll assume positive around the z-axis. So I've introduced 6 unknowns here, Pt, Mx, Mz, Vx, and Vz, and because I took everything to the right of my cut, in this particular example, there are no reactions, so I did not need the external free body diagram, although if you want to check this and take everything to the other side and find these values, you're going to get the same answers. However, you will need the wall reactions because you'll have the XYZ forces and the 3 moments at the where the wall is that we don't see in this picture. At this point, it's just a 3D rigid body equilibrium problem like we saw in chapter 5. Our method for solving those is we took the sum of forces in the 3 directions. Now we use our coordinate system. Along the x direction, I have Vx, and I have 150 from F2. Vx, then, I get a negative 150 pounds. In the y direction, I have negative P, since it's directed along the negative y direction, plus 350J, or 350 from F1. The internal normal force at point C, 350 pounds. It's positive, so we can say that this is in tension at this point. And finally, in the z direction, we have the Vz, minus 400 from F1, minus 300 from F2. So Vz, we're going to get a positive 700 pounds. Three internal forces we have now. So all that remains are the three moments, the two components of the bending moment and the torsion. Right, we wanted the moment around a point. I recommend doing it as a vector. So that moment around some point will equal the zero vector. Looking at the free body diagram, what point is the easiest to use? Right, just like when we had built-in connections in chapter 5 were usually the easiest. In this case, this is basically like a built-in connection. I have all my forces acting there, so I'm going to take the moment around C. On my right-hand side here, this is now, I usually like to account for the couples first so I don't forget about them, and then the moments due to forces. So what are the couples that are going to act at point C? Right, we have three couples here. It doesn't matter where we take the moment, they're still going to contribute to that moment. Let's look at mx first. mx is along what axis? Right, the x or it's in the I direction. Remember, when we do this vector method, everything needs an I, J, a K attached to it. So mx is around the I, mz is positive around the K. So according to our coordinate system, T is counterclockwise around the negative Y direction, so it's going to be a negative T in the J. These signs are determined by the coordinate system that we chose. T we drew in this direction because it was positive around the P axis. We didn't consider the X, Y, or Z axis, so that choice is going to be reflected here. So mx and mz we assumed positive around the axes to make this step easier. T, by convention, is negative here because P points in the negative Y direction. Those are the three couples we have in the problem. Now we have to account for the forces that act a distance away from C. By choosing C, that means that Vx, Vz, and P do not contribute to the moment. However, if we look at F2, that does contribute to the moment. Remember, we use R cross F and represent it as a determinant here. R, that position vector, always points from the point we want the moment about to the point where the force is being applied. So if we want to know the moment caused by F2, it will be 2 in the Y direction to go from C to where F2 is, or 0, 2, 0 in component form. And then the components of F2 we were given were 150, 0, and negative 300. And for the moment caused by F1, we have to go 2 in the J direction and 3 in the I direction to get there. That's 3, 2, 0. Or if we drew the actual coordinates down, which in this case I didn't, but usually in 3D I did. Using the coordinates, we could also find that that's going to be 3, 2, 0 to get from the point C to where F1 is. And the components of F1, we were given 0, 350, negative 400. Both of the forces were given in pounds. Both of these distances are feet. So our answer for mx, mz, and t will be all of them in foot-pounds. We want to make sure that we have consistent coordinates, or consistent units at this step. If we expand out these two determinants and group the like terms, just like in chapter 5, we're going to get mx minus 1400, or the I coefficient. 1200 minus t is the j coefficient. And 750 minus mz is the k coefficient. 750 plus mz. Setting each of our coefficients equal to 0 individually is going to give us mx is 1400 foot-pounds. T is positive 1200 foot-pounds. And our mz, we're going to get negative 750